Hello, class. This is MO 869, Introduction to Autonomous Vehicles. Lecture 3, Introduction to Perception. So far, we talked about autonomous vehicle technologies in general, but we're going to start the first module out of the 3 modules, which is the perception module. And this will be the introduction to that, the first module. All right, let's get started. So the outline goes as follows. What is perception? And then we'll talk about sensor configurations, and then perception tasks, challenges in perception, AI for perception, and then data sets. So what is perception? Perception is to understand surrounding environments. Information is acquired through sensors. Computer processes the sensor data, and things we need to perceive would be listed as follows. Dynamic objects, static objects, and then if there's any unidentifiable obstacles, then that would fall into another class. Dynamic objects include surrounding vehicle, truck, trailer, pedestrian, stroller, cyclist, motorcycle, and so forth. Static objects, lane, drivable road, traffic sign, traffic light, speed bump, crosswalk. So we need to classify as well as localize or detect where these objects are in 3D environment. Here, 3D is important. Compared to other computer vision tasks for autonomous vehicle applications and robotic systems, we need to perceive in 3D space. That makes things a bit more tricky. So to summarize the objectives of perception is basically 3D scene reconstruction. We want to be able to reconstruct 3D scene around the vehicle, including static and dynamic objects. And we also need to understand the scene. Understanding can mean a lot of things, but here, this sample image or slide shows a semantic segmentation results, which is to identify, first classify pixel level classes. So here we want to be able to identify what this pixel belongs to, and then that belongs to road, and then we want to be able to identify this pixel belongs to a car class. This would be pedestrian, this would be bus, car, this would be lane, and so forth. So there's this computer vision task called semantic segmentation, but from autonomous vehicle application, our goal is not simply to segment all types of classes, but things that are necessary and important for driving conditions, such as lane, road boundaries, drivable region, and then different objects. Those must be identifiable, so that we can understand the scene a little more than simple object detection. Since we need to understand what sensors are available for autonomous driving problems. Sensors are devices used to acquire the information about environments. Widely used sensors are camera, radar, LiDAR, ultrasonic. We briefly talked about sensors in the last lecture. And then there, when selecting and when we are dealing with sensor configurations, there are many things that we need to consider, but a few key attributes are field of view, which means angle through which the sensors can pick up information. And then there's resolution, smallest change that can be detected in the quantity that it is being measured. So one sensor may have large FOV, but then the resolution may not be so great. Another sensor may have, high resolution, but field of view may not be so great. So, we need to be able to keep track of these attributes when we talk about strength and weaknesses of different sensors. Here's the comparison chart comparing radar, camera, LiDAR. So we looked at this last lecture. If you take a look at the camera row, camera gives you good lateral position information. But the distance, longitudinal information is not so accurate. Actually, that information is lost when 3D environment is projected onto 2 image. So we can't really tell exact distance different objects are. But from the scene, from the context, position and size of the object, we can roughly tell how far it is. So that's why it's, triangle is used for that. And then there's range. What is the maximum distance the sensor can measure? And then there's cost, which is obvious. And then there's classification. It could be, pixel level or object level. There are different classification problems, but mostly, for autonomous driving, it's going to be mostly object level classification is absolutely necessary. And then there's weather sensitivity. Camera is not so great at weather and light conditions. So if it's really dark or if it's rainy, then camera perception performance will substantially drop. And then there's maintenance durability, which is good for a camera. And then there's radar row. Radar is pretty good sensor, except for classification and lateral information. So if you look at camera and radar, they are quite complementary, meaning that if one sensor is good at one attribute, then the other no, let me take it back. So if one sensor is weak on one attribute, then another sensor can actually cover that, meaning that another radar can actually be used to recover that weaknesses. And if you look at LiDAR, LiDAR is a very accurate sensor when it comes to accuracy. But if you look at other attributes, factors such as cost, classification, maintenance, durability, it's not perfect. Especially the major problem with LiDAR is its maintenance, durability, and cost. Those two are quite critical when using LiDAR for real-world deployment. More information is listed. So it gives you what are the strengths and weaknesses for camera, radar, and LiDAR. Please take a look at this slide on your own. I will have to move quick here. Sensors for full self-driving. Like I said a couple times, if we can truly achieve full self-driving, then we do not need driver, and we can do robotaxi type of service. So, which means that the business model allows the vehicle to use more expensive sensors such as LiDAR. This is how LiDAR works. I think I believe I described this in the last lecture, so I'm not going to repeat. But one of the key working principle is that we need some sort of laser transmitter, and then use a mirror so that we can change the direction of the laser emitting vector, so that we can scan 3D space and then reconstruct the 3D space. And that's where different technologies come in, and then one of the weaknesses also is coming from that part. So using this motor, some sort of, we need a actuator to actuate the mirror, so that we can scan the space. If you look at driver assistance systems, meaning that sensor suites, sensor configuration that is used for mass production vehicles, passenger vehicles. This is an example of that. You basically use all sensors, camera, radar, LiDAR, but mostly most of the vehicles only use camera and radar, but LiDAR is not quite widely used yet. Some high-end vehicles starting to use LiDARs, and we'll see how it goes. But like I said, from cost and maintenance, durability, reliability perspective, camera and radar is good for mass production vehicles. So it's multiple camera radars are used around the vehicle. When it comes to output, how radar output signal differs from LiDAR, this slide visualizes that difference. So we usually say radar gives you sparse point cloud, and you can see that right here. So LiDAR is a very gives you very accurate, dense, relatively dense. I mean, it's sparser than camera, but it's relatively dense, assuming you use high channel LiDAR, 3D LiDAR. Then you get this, multiple layer scanning, 360. So you have this, circular perception, or point cloud signals right out of the sensor. On the other hand, radar is providing. Let me move on. Yeah, let me talk about this first. The way automotive grade radar works is that radar antenna has this multi array type antenna. So when you have a signal reflected from an object, you get that signal received by multiple an array of antenna, and then you can tell by analyzing, by computing the angle theta, you can tell roughly where the signal is coming from, the reflected signal is coming from. And by analyzing, by signal processing those informations, and after Fourier transform, and then filtering, then you get point clouds. Looks something like this. So that's why you get this type of sparse radar point cloud. By the way, this is bird's eye view, top view image of the sensor outputs. But this is automotive application radar, and there are other types of radar, which is scanning type. So this one works similar to LiDAR. The way it works is it has very, very narrow field of view. So emits this radio signal to one direction with a very narrow field of view, and sends out very intensive high power radar beam. So the range is really maximized. So you can go up to kilometer level, and then you can receive a reflected signal and then be able to identify these objects. And then to obtain these information 360 degree, you need this scanning mechanism, rotating mechanism to get 360 information. So just keep that in mind, okay? And finally, we have camera, which is everywhere. We have cameras in phones, webcam, digital camera everywhere, right? The way camera works is we have this sensor, image CCD sensor, which receives light from the environment through a lens, and then gives you the intensity of the light. But there is three color, RGB, red, green, and blue. So we can identify intensity of how much light is coming in these three perspective, RGB, and then we can reproduce the scene. And because we are projecting, we are getting the image on a plane. It's a 2D plane image. The actual physical 3D space is projected onto this 2D space. So we lose the distance range information. So we need to somehow estimate, reconstruct that distance information using perception algorithms. And this is an example of automotive camera module. It's usually built front of the back mirror, the mirror you look at on your right upper side of your head. There's a back mirror looking at the back, and then usually there's a camera module behind that mirror. And this is a type of data you get from a camera, and the perception algorithm takes this input image data and to convert that into basically position of different objects, and be able to reconstruct 3D space around the vehicle. Okay. This is a Tesla camera module, just to give you an idea of what the camera actually looks like in real world vehicle applications as of now. So if you look, Tesla uses by the way, Tesla used to use Mobileye solution. They provide this perception algorithm, the perception model, camera-based perception module. But Tesla decided to develop their own camera-based perception system, and they are extensively using deep learning technology, developing rapidly recently, and they are heavily depending on images, camera. And for forward direction, they are actually using 3 cameras with 3 different field of view. So if you look at this, here's the wide angle, wide field of view for camera, and then there's main forward camera, and then there's a narrow forward camera. So there's a 3 camera looking at the front, because you really need to be able to tell where the objects are far ahead, as well as up close. So in CD scene, you need to look at wide field of view, as well as you need to be able to look really far ahead when you're driving on a highway. So one camera just cannot do the job. So they decided to use 3 cameras, and then they can cover wide range of field of view as well as distance. So they built 3 cameras with different lens. You can see this is 3 different lenses, and uses I think this is CMOS sensor, camera sensor. So they can look into the look forward with different views. And we'll talk more about how perception works using this multi camera input, and then outputting the a single perception results. Okay. All right, perception tasks. When it comes to perception tasks, there are a number of tasks. Let's go over one by one. First, the most obvious and very intuitive task would be 3D object detection, especially the moving objects. So when you think of the autonomous driving scene scenario, you will think of these objects that are around you, and you must be able to navigate through these objects. So naturally, you need to be able to detect these moving objects in 3D space. Okay. So you need to be able to identify existence, location, and class of the objects. Okay. And then there's a LiDAR-based 3D object detection. We can do 3D object detection using camera. We can do it with radar. We can do it with LiDAR. And obviously, the network, the model would be different. And the position estimation or localization problem is a regression problem from deep learning perspective, and we need to be able to regress these values. So XYZ would be position, center position of the cuboid, this box, 3D box, and then width, length, height, and then heading direction, yaw. Okay, and then there's class. And then there's tracking task, which means you need to be able to associate the detection results for different time frame. So the detection usually is performed on each frame, each time step, but you need to be able to track which object corresponds to which object at different time frame. so that you can create its motion. You can keep track of the motion of the object, and then you can predict its motion. And you need that information for planning purposes, okay, decision and planning purposes. So you need to once you after you associate, you usually assign object ID identification, and there's a birth and death of objects. So there may be new objects, and it's a birth, and then objects may leave the scene, then it's going to be a death. So you need to be able to do these things. And then there's semantic segmentation. One representative segmentation output would be lane and road detection. So if you think about it, in order for you to drive the road, the first thing you need to identify is the lane, okay, and the road. Otherwise, you can't do any. You can't go anywhere. You can't move at all. So, for instance, if you have lane and road information, and if you do not have 3D object detection, moving objects, you can do autonomous driving, when there are no vehicles, okay. But if you think about think of the other way around, meaning that you have moving object detection results, but you don't have these lane road information, then you cannot do anything, right? So I'm just emphasizing that this is very important. The first step towards autonomous driving, okay? And then there's 2D object detection. For autonomous driving, you need to be able to identify road signs and traffic lights at the minimum, okay? So that you can follow the traffic rules. And then there's depth prediction and then depth completion task. Depth prediction it's called a prediction because camera does not give you the depth distance information. You're predicting it using whatever the algorithm is, and we need that information either explicitly or implicitly. We'll talk more about this later on, but if you have depth prediction results, then you can do 3D object detection easier because you know the distance. So you can think of this as high density LiDAR outputs, right? So as long as this is accurate and robust, ideally, if we can do this accurate and robust, then it's supposed to be better than LiDAR. But the problem is that we are predicting using software, but we are only predicting and estimating, so it's not accurate. It's neither accurate nor robust. So for instance, when scene becomes dark, then the performance would substantially drop. Bad weather condition, it can also drop quickly. And as the distance increases, the depth estimation performance will also drop. Okay. So we can't completely rely on camera-based depth prediction results. And we need to, when it comes to autonomous driving, there's a safety issue. So we can't, unless we can rely on these results, 99.9%. It's not reliable. And then there's a completion task. What that means is, assuming you have LiDAR output, you can complete the depth image, such as these two, using both camera and LiDAR outputs. And that's called completion, because if you look at LiDAR output, it's quite sparse. So if you want to be able to obtain, complete dense depth map, then you need to do either depth completion or prediction. So you can do completion if you have LiDAR information. And lastly, we also want to do some motion behavior predictions. So when it comes to decision and planning, we need to be able to identify what the motion or behavior of moving objects are. So that we don't collide with these moving objects and make intelligent motions of the ego vehicle. We talked about different sensors, different perception tasks. So it may seem, doable, but if you think about, different challenging situations, you will feel that it's not that simple. So for instance, we are dealing with safety problems. So high accuracy and high robustness is mandatory to use for vehicles on a vehicle. So this makes a perception problem very challenging. But if you use LiDAR, or in fact, if you use multi-sensor, then we can have some redundancy, as well as LiDAR accurate LiDAR performance, along with camera and everything, and radar. Then these problems can be somewhat resolved. And robustness is also very important, because in real world environment, weather changes, illumination, lighting condition changes, there may be unknown objects, tunnel occlusion, rare events can happen. Okay. So it's quite challenging. And if you look at some of these sample, images, I guess this is quite extreme example, but others are pretty realistic samples, things you see once a while. Okay, and you need to be able to, a perception module needs to be able to identify what's going on here. What happens if you see this sign. How should you perceive it, what the perception output should be. If you look at this type of scene, how should you reconstruct your environment? What happens if police officer waves hand to you? How the autonomous vehicle should perceive and react? What if you see this type of vehicle, a vehicle on top of a trailer? They are all quite tricky, right? Is this two vehicle? Is this one vehicle? And so forth. And then there's more tricky samples. At nighttime, you may see animals crossing the road. You may see bicycle at the back of the vehicle. You may see these type of horse carrying the carriage, and so forth. These are all quite tricky samples, and perception model needs to be able to identify what's going on. And another problem is that if we have a large model and tons of data, then maybe we can solve these tricky problems. But the problem is we need to solve this in real time. Okay, meaning at least 20 frames per second. Okay, and this can be quite challenging problem. And we also need to do multiple things, multiple tasks. We talked about different tasks, and we need to be able to learn different tasks, okay, and output them in real time. That's quite challenging, okay. So, but if you look at these tricky conditions, and if you use LiDAR, then many of the problems become a bit easier, okay? Because the LiDAR gets the ranging information and the point cloud, and then you can tell, you can exactly tell there is an object or not. The size, position of the object can be quite reliably estimated. But we talked about weaknesses of LiDAR, right? So like I said, LiDAR is almost always used for level 5 autonomous vehicles, but level 3 or level 4, maybe we can get away with LiDAR. So, and that's because usually level 3, level 4 autonomous vehicles are usually used for mass production vehicles. All right, let me stop here and let me continue next time, okay? All right, let's continue. So far, we covered up to here. So we talked about these 4 bullet points, and then let's talk about these 2 bullet points. AI for perception and then data sets. Well, if we start introducing AI, we have to start with deep learning. As everybody is already familiar with, deep neural network. It's a high-capacity model with a large number of parameter weights, strong approximation capability, end-to-end training. And just to give you a quick background on deep learning, there's a theory called universal approximation theorem. Let's go through this line by line. A feed-forward network with at least one hidden layer can approximate any Borel measurable function with any desired non-zero error, provided that the network is given enough hidden units. So what that means is, these neural network can approximate any function, Borel measurable function. Here, the tricky part or the hook is this part, enough hidden units. So what that means is we can, if we assume that we can use infinitely many hidden units, then we can approximate anything. So it's very general statement, but still this gives a foundation for deep neural network or any neural network based models. So the problem, this is fundamental theory, but there were many practical issues, which we'll discuss all of that in the following lectures as well. The following lecture will cover introduction to deep learning. So we'll talk a little bit more about these in detail. And then another concept here is hierarchical feature learning. So as we make the network deep, the deep learning discovers multiple levels of representation, hierarchy of features from lower level features to high level features. Why are deep models better than shallow models? Deeper models can reduce the units required to represent the specific nonlinear function, and thus can reduce the generalization error. So this slide introduces the deep neural network. So here, this is general theorem, such that even one hidden layer can do this job, can approximate any function. But when we have one layer with many units, usually it's not very efficient from a modeling perspective, as well as it's difficult to train. And as we move towards deeper models, there are many advantages. And here, I'm introducing this concept of hierarchy of features. So each layer can learn different types of features from low level to higher level, more abstract features. And technically, this is easier to learn, to train, and this is much more efficient than shallow models. And let's talk a little bit about representation learning. Conventional machine learning framework looks something like this. So we have feature extraction module, and then the feature extraction module extract feature from the image input. And this feature was mostly handcrafted in the old days. And then we have a classifier that classifies, whatever the task is. The classifier classifies the input image using these features you get out of the feature extraction module. Here, the key is that the deep learning does not require this handcrafted feature extraction model. Instead, we can do end-to-end learning. So, and like I said, we'll talk more about these in the next following lecture. Okay. Limitation of conventional model-based algorithm are listed as follows. Use the analytic models to describe the data. Use the handcrafted features for perception task. Limited to describe the true data distribution well. On the other hand, deep learning-based algorithms can learn the data distribution from data, better at learning complex data structures, and generalize better to data variations. But here, the key is data distribution from the data. So this is often called, current state-of-the-art deep learning is sometimes called a data-driven approach, and that's because it heavily relies on the data set. And then there are two stages of deep learning. The first stage is training the model, and then we have inference stage. So in the training stage, you train the model using the training data samples. And there's a long optimization period required. For different inference, deploy the trained model and try unseen data. Real-time operation is often required for inference stage. And let's move on to data sets. So today I gave you a very brief introduction to deep learning, but I'll talk more about these in the following lecture. Let's move on to data sets. Data set is a collection of sensor data with annotations for training, validation, and test. Important aspects are diversity, quantity, sensors, benchmark. Here, the important part is actually this diversity part. Usually when people create data sets, it's easy to come up with a large data set, but guaranteeing diversity is quite tricky, because you can't tell from the data right away that you have sufficient diversity from the data set. I mean, from a human perspective, you can, for example, you can say it's diverse because you collected data when you collected data when the weather is warm, hot, cold, and then you collected also data for nighttime, daytime, rainy scene, but those are just basic diversity criteria that human actually can tell, but there's much more than just weather and lighting conditions. There's all kinds of background when it comes to autonomous driving conditions, and there's all kinds of objects. There's all kinds of occlusions, distance, uphill, downhill. There are just so many scenes that you can imagine, and sometimes things that human cannot tell may require diversity as well. So this is quite tricky to quantitatively measure it. And then when it comes to data sets, obviously you need to set up a sensor suite, sensor around the vehicle. And then you also need to define the tasks you are interested in. So for annotation and inference purposes. So different data sets have different sensor suites, different tasks, different quantity, different diversity. So let's take a look at different types of data sets. Let's start with Kitty dataset. The Kitty dataset is the oldest dataset. I think this is the first dataset for autonomous driving applications, and then it moved on to other datasets. People started to publish different datasets for their needs. Nuisance is collected and published by autonomy, which is active and motional now. And then there's Waymo, Google, and then there's Argoverse from Argo. They were acquired by, I believe, Ford, but then they decided to shut down the autonomous vehicle department. And then there's Lyft, which is a Uber type of company. They also published a data set. And then there's ONCE, Apolloscape, Cityscape, Berkeley Deep Drive, and then Oxford University data sets. Each data set has different sensor configurations. Some has more camera, some has more LiDAR, some don't even have radar. And some data sets do not have map in their data sets. And here's the number of annotated frames. So as you can see, Waymo, Apolloscape, Argoverse, in Berkeley Deep Drive, they have pretty large number of frames, but Berkeley Deep Drive do not, have these LiDAR, radar, map information. So it's not very useful for autonomous driving applications. It was mostly collected by computer vision lab, so they focused on the image data set. So you can this slide, this chart summarizes different types of data sets from the sensor data perspective. And then there's we can categorize by different tasks. As you can see, there's 2D tasks, 3D tasks, and some data sets have many tasks. They offer many tasks, such as Kitty, and then Apolloscape, and then I think new scenes. They provided a pretty good number of tasks. So if you're interested in, for instance, if you're interested in, stereo optical flow type of task, 2D task, then you will need to use either Kitty or Oxford robot car data set. On the other hand, if you're interested in 3D object detection, which is the most basic popular task, moving object detection, then many of these data sets offer those type of annotations and benchmark. So depending on what you're interested in, you may need to select one data set over others. But when it comes to so for research purposes, you can just simply select one or more data sets for your research. But then if you ever have to consider integrating your algorithms, then you would need one data set that offers many different tasks. Okay. So the most popular these days, the most popular data sets are these two, Kitty and Nuisance. But the problem with Kitty dataset is the map information is not provided. Plus, the data set is quite small. Let me go back. Yeah, KT does not provide map, and it has low number of frames. So KT is relatively small. It's one of the first data set, but so it's small. And sometimes people claim that you can get overfitted, meaning that you can get very good performance within the data set, but in real world you don't get that type of real world performance. All right. So let's go over these data sets. There's the first one would be the most popular data set, KT data set. The sensors are listed here. High resolution stereo, Velodyne, which is relatively old, LiDAR, and then there's many different computer vision tasks. And then the key features are, this is the first data set for autonomous driving with leaderboard and long history. Relatively compact data set, good for academia. In other words, you don't have to have huge computing power, which often is not available in university environment. So it can be overfitted. The model can be overfitted. And let's move on to new scenes. This is released by Aptiv Motional. This one, I think this Aptiv collected or created this data set with mass production in mind. In other words, they adopted radar. They used 5 radar. 1, 2, 3, 4, 5. 1 for facing front, and then rest 4 are mounted on each corner. And then used relatively low channel LiDAR, which I believe they believe that low cost LiDAR is practical. And then there's many different tasks for autonomous driving requires. It's not shown here, but they also provide map, which is quite important, which is not in the KT data set. And this was the first data set with radar point cloud. So that makes nuisance special and differentiates from other data sets. So if you are going to use radar for your perception task, then you almost have to use nuisance. Okay. And then there's Waymo data sets. Waymo released their data set relatively late, but because they they have long history of developing autonomous vehicles. They can collect large amount of data sets from their fleet of autonomous vehicles. So as you can see, it offers 200,000 annotated frames, which is the largest. And then they use multiple lidars. As I mentioned last time, Waymo heavily relies on lidar technology for their perception models. So these are some of the key features. Okay. And then there's Argoverse, released by Argo AI. Sensors are 2 lidar, and then 7 ring cameras, looking at 360, and then 4 stereo cameras, and then includes vector map and rest-wise map. So Argoverse also provides a map, which is not always provided for those data sets. So this would be one of the key feature Argoverse offers. And then there's lifts. I'm not going to go through every single data set, but just keep in mind that there are these other data sets you might need to take a look when you do research. So there's lifts ones. There's Apolloscape. Apolloscape is released by Baidu. So this is Chinese data set. And one of the key feature is that it provides 3D segmentation data sets. And then there's Cityscape. Like I mentioned briefly, this data set doesn't offer many tasks. It's mainly for computer vision, semantic segmentation task for city environment. And it provides these image view semantic segmentation or instance panoptic segmentation tasks. So it's somewhat limited when it comes to sensor as well as task. And then there's Berkeley Deep Drive. This is also quite limited. Uses 1 camera, and then tasks are also quite limited. And then there's Oxford University dataset. One of the key feature of this dataset is that it uses radar scanning type radar data set is provided. So the new SINs use automotive grade radar, which uses the array type antenna. But this data set uses scanning type radar. And then this data set was initially used for their localization problem. So, SLAM type of problems. So they wanted to do, localization, solve localization problem using radar sensor. So that's pretty different from prior data sets or research work. Okay, so that's it for lecture 3. So this concludes lecture 3, and let me move on to lecture 4, which is Introduction to Deep Learning. Okay. Thank you for your attention.